Hey everyone, this is a supplementary video that serves as an extension of the Maxwell's EM Unification syllabus dot point in Module 7 of the HSC. Now it's important to note that this video is only aimed at those looking to gain further insights beyond the HSC syllabus, but I do think that the approach I'm going to be using to interpreting Maxwell's equations can serve to just foster a universal appreciation for really anyone with science or mathematics experience at the high school level. So I guess a good place to begin would be to look at these equations, and this is them in their differential form. You've probably heard about how they serve to provide a unified theory of electricity and magnetism. Now, you've probably been told to just don't really worry about the first two equations, and that's what those asterisks mean there. And that's because these equations are not really useful to us in terms of our HSC syllabus. And the reason for that is because we're learning these equations in the context of how they predict the production and propagation of electromagnetic waves. Now, if this doesn't ring a bell, let me briefly get you up to speed. So you've probably heard that oscillating charges give rise to electromagnetic waves. How do they do this? Well, they produce electric fields which propagate outwards from the charge, which by Ampere-Maxwell's law, that fourth equation, well, now we have a changing electric field, and then, so because we have a changing electric field, it predicts that we're going to get a magnetic field. It's going to induce a magnetic field perpendicular to it, and that's our electromagnetic wave. And then by Faraday's law, that third law, well, now we have a changing magnetic field, and so that changing magnetic field is going to induce a perpendicular changing electric field. And so really these electric and magnetic fields propagate each other as EM waves. And that's all you need to know for the HSC, and that's all well and good. But it is quite hand-wavy and quite unsatisfying because you're not really understanding how the equations themselves can give rise to these predictions on a quantitative level. And probably the thing that looks the most intimidating are sort of the symbols, the like upside down triangles symbols. So I'll sort of label those. So these right here are your vector operators, where the first one is your vector operator for divergence and the second one is curl. And now, of course, it'd be quite an impossible task to understand these mathematically because, well, you'd have to learn vector calculus. So I'm going to skip through going through the rigor of these equations. I think what is more valuable, though, is to understand these equations, and I think there is a way that we can understand these with a tangible mathematical framework. And the way I want to go about doing that is by looking at these equations in their integral form, like this. And then after we've sort of looked at our findings from this, then we can apply it to understanding the language of divergence and curl. So I guess let's start here. Now, I think looking at it like this is better because it's written in a mathematical language that we're much more familiar with. It's the language of integration, and even though I'm aware that calculus is not a prerequisite of HSC physics, I think everyone really, with a bit of training, has a vague understanding of integration as a sum of the infinitesimally small, and I think that's all you need. Now, if you're looking a bit closely, you'll notice that the first two equations are not built the same as the third and fourth, as they are integrals in terms of dA. So the first two are sort of integrals in terms of dA, and the second one are integrals in terms of dL. And so let's begin by understanding the first two equations. I think we should start by understanding, I guess, the problem we're trying to solve in the first place. So you can think of this as the left-hand side of the equation, where the right-hand side is the answer to that problem that we're trying to solve. In particular, the second one is a concept you might already be familiar with. It might look a bit familiar, but if you're not really seeing it, let me help you spell it out. Now, if you've done vectors in high school, you'll know that this symbol right here is a dot product. And what a dot product is it's sort of like a way that we can multiply vectors. So if you have two vectors, A and B, like shown, with some enclosed angle theta, then we can multiply them somehow by finding their dot product, which is equal to their magnitudes times together, times by cos theta, where theta is that angle enclosing them. So I can really rewrite this equation here as b times dA, b dA cos theta, right? Now let's have a think about what these variables mean. So theta is obviously the angle enclosed by B and A. B is magnetic field strength, as you guys know, and A is area. Recall that area is also a vector with a direction, which we'll talk about in a second. Now, if I'm dealing with a constant theta and a constant b, then I can move these out of the integral to get a more simpler problem of b cos theta times the integral of dA. And so now all we have to do is sort of solve this part. So if you consider a rectangular coil with some area, right? And so really dA is asking us to take a delta A, right? A really small piece of that area, an infinitesimally small chunk of area. And that integral sign is telling us to, hey, let's take the sum of that area. Let's take the sum of all of those infinitesimally small chunks over the entire area. And so I guess this equates to A, and we get BA cos theta. BA cos theta, that is magnetic flux, which is in the HSC syllabus and is something you should be familiar with. And so what we see is that really the second equation is one that describes magnetic flux, and the first one, is one that describes electric flux, which we haven't really dealt with before. Now, what is flux? Well, recall that flux, all it is it's referring to the amount of field lines passing through an area. And so what we see is that we can increase this by increasing the magnetic field strength B. So if we increase B, well, let's say we have some magnetic field lines like this. Well, if we increase B, we're increasing the amount of field lines, we're increasing the density of field lines like this. And so yeah, we do see that we get more field lines passing through. And there's also another way to increase the flux, which is by increasing A. So if I increase the area in which I'm enclosing those field lines, well then more field lines can sort of pass through. And so I'm also increasing the flux because I'm increasing the amount of field lines that can pass through. So there's sort of different ways to increase flux. Now you're probably also wondering what this circle is. So I've sort of been like ignoring this. And what the circle means is that we're integrating over a closed surface. Now you've probably never worked with something like this before because you've never really integrated something in 3 dimensions, which sounds intimidating, but I promise in this context, in the simple context that we're going to look at it, it's really not that intimidating and it's totally stuff that we can do. And to illustrate this, let's actually think about finding the electric flux through a closed surface. So what is a closed surface? Well, it's just essentially a surface that doesn't extend towards infinity. So for an example, a good example of this might be a sphere. So let's consider finding the flux through a sphere. And let's say we put that sphere inside of an electric field. Right, so let's find the electric flux. So the first problem, let's solve the first problem for the case of an imaginary abstract sphere. Now recall that area is a vector and it has a direction, and that direction is normal to the surface. So have a think about what the sphere's area vector would look like. Well, it'd probably look like this, right? Where all those vectors are perpendicular to the surface. Okay. Now let's consider the electric flux for an electric field line entering the sphere. So let's isolate this electric field line. And so if we're sort of looking at the component of area that is parallel to that field line, well, they're in opposite directions. Recall that a dot product is really, we're trying to solve E dA cos theta, and we're trying to find the integral of this. Well, cos theta, what is theta? That's the angle between the vectors. They point in opposite directions, so theta is equal to 180. So really we're trying to solve cos 180. Cos 180, that's a -1. So this is equal to negative E, where the integral of dA is A. Oh, actually, let's consider it for that infinitesimally small piece of area. So let's say it's just E dA. So we're considering the flux through this tiny piece of area dA. And so really that field line contributes negatively to the flux. And let's trace that field line leaving the sphere. So this one. Well, then in that case, we sort of have a component of the field that is in the same direction, right? And so now our theta is going to be 0. And so really we need to solve cos 0, which is 1. And so leaving the field, we get an electric flux of E dA. And so here it contributes positively, and entering the sphere, it contributes negatively. And so the net flux contributed by that electric field line is 0. And similarly, I could do this across the entire sphere, pairing these positive and negative contributions, and what I'd find is that I'd get 0 net flux. And this is really consistent with our understanding of flux as the amount of field lines passing through something, because the same amount of field lines passing through the sphere also leave that sphere. So there's like no flux, right? There's no net flux through that sphere. So I guess my next question would be, how is it possible to get a non-zero flux? Well, what happens if I place a charge inside of that imaginary sphere, like shown? Well, in this case, I sort of have a high density amount of field lines passing through the sphere, and I have less dense field lines passing out of the sphere. And so that is, I have more field lines entering the sphere than I have leaving it, and so I should have a net flux. And we can think about this mathematically too, right? Let's consider the area vector. Well, what do you notice about the area vector and the field lines? They're parallel, right? And so really in my problem, I have E dot dA, so E dA cos theta, finding the integral of that. And what is my theta? Well, my theta is going to be 0, right? There's no angle between these lines, and so my cos theta is going to be cos 0, which is just 1. And so now I'm solving a much simpler problem of E dA. And in fact, this electric field, right, I have a way that I can express this. Well, recall that electric field is equal to the force experienced by another charge in that field, and it's independent of that charge. So what is the force experienced by another charge? Well, that's going to be 1 on 4 pi epsilon naught times by Q times that other charge, let's call it Q dash, all over R squared. And it's independent of this Q dash, so let's delete it. And so this is really our electric field strength. And so let's sub that in. So we have, and it's constant, so we can take it out of the integral. So let's just write it on the outside. So 1 on 4 pi epsilon naught times Q on R squared times by the integral, the surface integral of dA. And hey, if we're taking these infinitesimally small pieces of area, let's say this one, and I'm finding the sum or the integral of this across the entire surface, then that's just the surface area of a sphere, right? What is the surface area of a sphere? Well, it's 4 pi r squared. Hey, I have 4 pi r squared up here. That cancels out with the 4 pi r squared down here. And so I get an expression for my electric flux, which is Q on epsilon naught, where Q is my charge enclosed within the sphere. So we say it's Q enclosed. So I get an expression for the electric flux through this imaginary sphere. And surprise, surprise, this is actually how Maxwell, this is Maxwell's first equation, right? We've just derived it. And so I think we're ready now to reframe this in terms of the language of divergence. So let's actually look at its differential form. Now the difference is, though, with these equations that we want to describe the electric field at a single point, whereas before we were describing it over the surface, we want to describe it at a single point, where divergence tells us how much the electric field diverges away from that point. So let's say we have an electric field. Okay, we have a point. Well, hang on, if I sort of zoom in on that point, well then I just get a problem that's analogous to before, right? Where my net flux was 0, and those field lines, they don't diverge away from the point. So we say that my divergence is 0, right? So divergence is sort of analogous to electric flux, except it just applies for a single point, right? Sort of describing the electric field at a single point. It's just the mathematical language that we're going to use to help us describe this. Similarly, in our other case, right, of the electrostatic field produced by a stationary charge, if I consider what happens at a point and I zoom in on that point, well, I just get a problem that is the same as before. And recall, I had a net flux before, I had a positive flux before, and so similarly, I have a positive divergence, which makes sense, right? Those field lines seem to diverge away from that point, and so really divergence is something that we can really make sense of on a qualitative level. And really, all divergence is telling us is the extent to which the field lines diverge about the point. So if I have a divergence that is greater than another divergence, then that means that that field diverges at a greater extent. Now I want us to take a closer look at this equation. So instead of Q enclosed, we sort of have this other symbol, we have rho, and rho means charge density. And so in the non-zero divergence case, so the case on the right-hand side, we are enclosing some electric charge with charge density rho, and really what this equation does is it says that exists some electric charge that is capable of giving rise to electric fields. That is, this equation, what it's doing is it's relating the electric field to the charge that caused it. Yeah, and so now I think we should consider what happens if we replace these electric fields with magnetic fields. So let's look at the case of magnetic flux. Well, okay, we get zero divergence in the left-hand case, sure, but is that right-hand side case even possible? Well, recall that what we needed to do was enclose a singular charge. But hang on, can we get magnetic charge? Recall that magnetic monopoles don't exist. That is, we can never isolate just a single north pole or a single south pole. We always get dipoles with north and south poles. And so the right-hand side case can't happen for the case of magnetic fields. That is, there is no magnetic charge that can cause a B field. So we can't relate magnetic charge to a B field because it doesn't exist. And that's why the divergence of B is always zero. It's because that right-hand side case is not possible. Okay, now let's look at the third and fourth equations. So these ones here. And once again, we'll start by looking at the problem, so the left-hand side. Now, as you guys know, that fourth equation has something to do with how electric fields give rise to magnetic fields. And so what better case to look at than the classic one of Ampere's law that we're familiar with, where we have a charge-carrying conductor and we're considering the magnetic field produced by it. So let's consider that we have sort of a current going into the page, and by the right-hand grip rule, right, the field lines produced by that current are going to curl around, right, and critically it's going to curl in the clockwise direction as shown. Now, the problem we're trying to solve here is different in nature to the previous one because we're integrating with respect to dl, which is an increment of a line rather than an area. And so we're not integrating over, I guess, a three-dimensional surface, but rather a one-dimensional one. Perhaps a two-dimensional one, rather. Because we want to integrate over a closed line. And what simpler case of a closed line than just a circle? So instead of imagining a sphere, let's imagine a circle, right? And I'll draw that circle in. And what we're considering is integrating in terms of an infinitesimally small piece of that circumference, dl. Right. Now, if you consider the magnetic field around that sphere, well, all the lines are tangential to that sphere, right? All the surrounding magnetic field lines are sort of tangential to that sphere, like this. And so what can we say about the angle between dl and the magnetic field? Well, at every single point, at every single dl, right, the theta is going to be zero. There's no angle between dl and the surrounding magnetic field lines. And so once again, we get the problem of saying, cos theta, where theta is equal to 0, cos 0 is 1. And so we can simplify our problem, our fourth equation, as b dot dl as b dl, b times dl, cos theta, where cos theta is equal to cos 0, which is equal to 1. And so now we're solving a much simpler problem. And in fact, we can take magnetic field out, right? That magnetic field strength is going to be a constant value. And we have an expression for that value. Recall, the magnetic field produced by a charge-carrying conductor is mu0 times I on 2 pi r. And so now we need to solve this second problem of finding the integral around the loop. Hey, we have these infinitesimally small pieces of the circumference dl. If I find the sum of this across the entire loop, that's the same as finding the circumference of the circle, which is just 2 pi r. And so, hey, I sort of get 2 pi r, and they cancel out. The top and bottom cancel out. And so I get that this is all equal to mu0 times I, where once again, that I is sort of like the enclosed current. And so I get an expression for my line integral of magnetic field strength. So now we need to talk about the third equation. And in the case of electric fields, let's say I was talking about having a stationary charge, which I'll use a different color for. maybe orange. So let's say I replace this charge carrying conductor with like a charge with field lines going like this. Well, what do you notice about those field lines relative to the circumference? Well, they form 90-degree angles with that circumference, don't they? Right. And so our problem is going to be b times dl cos theta, but cos theta is going to be equal to 0. And so this whole thing goes to 0. And so even though before, right, that case of electrostatic fields was quite a useful one, in this case it's not very useful at all, right? It's not very useful. We should consider a different case when we're talking about line integrals of the electric field. So before I talk about that though, recall that electricity and magnetism are really just a unified interaction. That is, they are the same thing, just viewed from different perspectives, with neither one being the more fundamental interaction. That is, they can be defined from each other because all of it is self-consistent physics. And I think the best example of this is one we looked at in class, where we have this magnetic field going into the page. And let's say I move a rectangular coil into that field. Well then, at some time later, right, we're going to have one of those sides inside of the field. And hey, one of these sides is just a charge-carrying conductor, right? That charge-carrying conductor is moving into a field. Well, if I have a conductor moving into a field, it's going to experience the motor effect force, right? And if it experiences the motor effect force, well, let's consider for one of those charges inside, right? We have sort of this charge here, it's moving with a velocity to the left, with field lines going into the page, and so that charge is going to experience a force downwards. And so we're going to experience a current, and that current is going to go around the loop in a counterclockwise direction. And so we can explain it like that. We can also explain it using Faraday's law, right? We get a changing magnetic field into the page, and so by Lenz's law, this should produce a current that is out of the page, which is a counterclockwise current. We can use the right-hand grip rule to derive that. And so there's sort of two ways to go about explaining this. One using a Faraday's law method, and one using sort of a F equals QVB method, one in terms of the electric fields. Now this is all well and good for this case, but what if there is no relative motion? So let's say I have a coil here, and I just turn on a magnetic field like this. Well, there's no relative motion, so there's no QVB forces going on, right? There's no V. So how can I explain this, right? I can explain it using Faraday's law, sure. A changing magnetic field into the page by Faraday's law, this should induce an EMF, which produces a current, which by Lenz's law should oppose the changing magnetic field, which is out of the page, and so I should get a counterclockwise current. And that's all well and good, right? So I get a current that goes like this, and that's fine. But what about an electric field explanation? Well, clearly, to get a current to flow, those charges inside the coil must experience some kind of electric force that does work on them. That is, in the case of the changing magnetic field, what we're really doing is we're inducing an electric field around the coil. Now have a think about the direction that that electric field must run. If it's causing those charges inside the coil to move, then that electric field should be circular, right? It should run concentric to that ring, such that it produces an electric field that sort of moves the charges around that loop. And so this does a work on the charges, right? It does a work on them around the loop, and recall that work is equal to W equals Fs cos theta, where F is my force and S is my displacement. Now you've probably never thought about it this way, but really this is just another dot product, right? It's just F dot S, because we have something times another thing times cos theta. If you're considering the work contributed by an infinitesimally small piece of coil dl, well then that's just going to be F dot dl, right? And so to find the work, to find the total work around the entire coil, well then that's the problem of F dot dl with an integral sign in front of it. Now that force is an electrostatic force. Recall that we have an equation for electrostatic forces, which is QE, right? F equals QE. And that Q, let's say it's for a constant charge, right? An electron has a constant charge inside that coil, and so we can take that Q out. And so now I've reframed my problem into what I want, right? E dot dl. That's the problem that I'm solving for. And so let's subject for it, let's divide through by Q, so I get W over Q. Hang on, W over Q, that's just voltage. Voltage is not just any voltage, we're inducing an EMF, which is predicted by Faraday's law. And it's not just, and because we have an EMF, right, that's just the rate of change of flux. That's just negative d phi on dt, where phi is my magnetic flux. And so this is going to be equal to E dot dl, which is the problem that I'm trying to solve for. So this is the solution to my problem. And so that's exactly what Maxwell's third equation is. Okay, so I think now we're ready to consider the differential form of these equations. To reiterate, these differential equations describe the nature of a field at a single point in space. But instead of using a sphere, we're really integrating around a small circle around that point, because this is, now we're talking about line integrals, right? If we're thinking about the integral equivalent of these equations, we're working with line integrals. Now it's important to note that while in Mod 6 we covered electric fields as these arrows which extend out towards infinity. So, you know, we know that electric fields look like this. Really, when we're working with vector calculus, we're working with the vector field. And so what this looks like is we're considering, hey, at this point, what is the electric field? Well, maybe it looks like this. At this point, what is the electric field? Well, maybe it looks like this. This point might look like this. This point might look like this. This point might look like this, right? We're considering different points in space and what the electric field looks like for a test charge at that point. So yeah, that's a critical distinction to make. And as it turns out, for a changing magnetic field, the induced electric field around every single point on, let's say, an imaginary circle. So let's say we're sort of, let me let the GIF play out. Okay, so let's draw an imaginary circle. Let's zoom in on it as we did before. Okay, and let's say we have this changing magnetic flux, which is represented by the orange vector. Well then, for every single point around that circle, we're going to get a changing electric field that curls away from the center of that circle. And so, hang on, curl, right? That's just that vector operator. And so really that vector operator is describing the scalar strength to which the vectors curl around the center. And this symbol here, well, that's just a partial derivative, which is the same as a derivative when we're ignoring other variables. And a derivative is a change in something, so this is just a mathematical way to calculate the change in magnetic field over time. And of course, magnetic field is very closely related to magnetic flux, which is the form in which we sort of had the equation before, right? We were describing it before as a d phi over dt, but this time we're relating it to the magnetic field strength instead. And so, yeah, these equations are very closely linked together. Now, let's look at the fourth equation, Ampere-Maxwell's law, which is the scary looking thing. Now, we're already quite familiar with how electric current can produce a magnetic field. So, you know, here we have an electric current going down the page. Let me draw my imaginary circle, and let's look at every single point on that circle. Well, I'm going to get a magnetic field, right? And that curls around the center critically. And that's what the first half of Ampere-Maxwell's law says, except it's in terms of this funky thing here, which is J. And J is just current density. So before we related it to current, mu 0 I, and so now we're relating it to current density, which is just the amount of current in some area, right? And that's very closely related to I, so they're really saying the same thing. But it's important to note that Maxwell had his own contribution to this law, which is this second one. And critically, that second part is very important to our understanding of this law, because changing electric fields, producing changing magnetic fields, that's exactly what we need to explain the production of electromagnetic waves. So we really need to understand this. But in high school, we've never really dealt with changing electric fields over time. So except for maybe in like AC, right? So let's work with AC, but how do we produce a uniform changing electric field? Well, let's connect them across parallel plates such that we have this uniform changing electric field like this. So we get this uniform changing electric field. Let's draw imaginary circles around it. And so now we get these curling magnetic field vectors once again, except this time they're changing direction. And in fact, this is the same across the entire gap between those plates, right? And so what we observe is a uniform magnetic field that curls around, if you will. And so that's really what Ampere-Maxwell's law is saying. And so just like that, we've sort of understood these equations on a more deeper level by first looking at their integral form and working with the maths behind these equations. And then after that, we sort of reframed it in terms of the language of divergence and curl to sort of gain further insights into what they mean as describing the field around a point. So that's what we did today, and I hope you enjoyed the video. I hope this was useful, and enjoy the rest of Year 12. Thanks for watching.